This is a continuation of a series of videos that I'm making to support a course that I'm teaching in introductory proofwriting. So far we've looked at the method of direct proof, a proof by contrapositive and contradiction, as well as some assorted examples. Today we're going to look at the principle of mathematical induction. And mathematical induction is an excellent way to prove a family of statements which depend on each other and they depend on the natural numbers. So I've written it up here like this. So let's say we've got P of n, and those are all mathematical statements depending on a variable n, which is a natural number. So in previous videos, we looked at what exactly a mathematical statement is and what mathematical statements depending on variables were. So this is the type of proposition that you might want to use mathematical induction for. So it says for all n in the natural numbers, P of n is true. Although sometimes this is true is left off, most of the time when you say a mathematical statement like P, Q, P of n, it's assumed that you're talking about its truth. So here's an outline for the proof. So you want to start off by proving something called the base case, and that is establishing that P1 is true. So you've got this whole family of statements. You can look at what the first statement is and prove that that statement is true using any method that you would like. Generally, that base case is a pretty easy calculation though. Next, you'll prove a certain conditional statement known as the induction step. So you want to prove for some arbitrary k, which is a natural number, that pk implies pk plus 1. So sometimes this is broken down into something called the induction hypothesis, where you suppose pk is true, and then the induction step where you use that to prove that pk plus 1 is true. But you could also write it like this as an implication. And here I'm being a bit sloppy because often you also use the base case within this induction step. So you're not just assuming pk, but you're assuming pk and p1. Sometimes you're assuming quite a bit more if you're doing something called strong induction, but that's going to be a future video. So why does this work? Well, notice you started by proving P1 is true, and then the fact that PK implies PK plus 1 tells us that P1 implies P2, then P2 implies P3, P3 implies P4, which implies P5, and so on and so forth, making every statement true. So I think we're going to do about 5 examples involving proofs by induction. So my whole philosophy is you should maybe do 1 or 2 more examples than you feel like you need, just so that everyone has the chance to really get an idea for what's going on. And whenever you're studying for an exam or practicing a certain type of problem, I think that's good advice as well. Do 1, 2, 3 more than you feel like you should do, and then you know that you've really got the technique down. Okay, so let's say we want to prove this statement. For all natural numbers n, 1 plus 3 plus 5, all the way up to 2n minus 1 is equal to n squared. In other words, the sum of the first n odd natural numbers is a perfect square, and it is in fact n squared. So let's outline what our statement is. So our statement, P of n, is this thing that says 1 plus 3 plus 5 all the way up to 2n minus 1 equals n squared. So if we're following this outline, we want to show P of 1 is true, and then we want to show this implication. So let's see if we can do that. So I'll first start off with the so-called base case, which, like I said, is establishing the truth of P1. But notice this is clearly true because we have 1 equals 1 squared. And notice that's exactly what you get for this first statement. And like I said, a lot of times these base cases are very, very simple calculations. Okay, so now let's prove our induction step. And so that means we want to suppose for some k, pk is true. So let's do that. So suppose for some k bigger than or equal to 1, 1 plus 3 plus 5, all the way up to 2k minus 1 equals k squared. Okay, so like I said, right here, we are assuming that pk is true, the kth statement. Next, what we'll do is show that, okay, so now we're ready to make the calculation to show that pk plus 1 is true. So generally, I like to maybe use the word like consider. And so we're going to consider the object 1 plus 3 plus 5 plus all the way up to 2k minus 1 plus 2k plus 1. So notice that's the sum of the first k plus 1 odd numbers. So we can group these and apply the induction hypothesis, and that's going to give us k squared plus 2k plus 1. Again, that's just by applying the induction hypothesis to these first k terms. But that's clearly a binomial squared. We can write this as k plus 1 squared. But this equality, or this string of equalities, is exactly the k plus first statement. And what did we use to prove the k plus first statement? We used the kth statement. So we've proven this implication. But that implication, along with the base case, means that this statement is true for all n. So you might want to finish this thing off with something like, by the principle of mathematical induction, which on the board I'll write as PMI, we have 1 plus 3 all the way up to 2n minus 1 equals n squared for all n, which is a natural number. And that finishes off this proof. Okay, so let's jump into another one. Now we're ready to jump into our next example. So that says for all odd natural numbers n, we have 3 divides 2 to the n plus 1. So in other words, 2 to the n plus 1 is a multiple of 3, or 2 to the n plus 1 is congruent to 0 mod 3. Although we won't work with modular arithmetic, we'll work with the notion of being a multiple of 3. So let's maybe go ahead and jump into this proof with the base case. So like I said, the base case will be the first case. In this case, it'll be the first odd number, which is when n equals 1. So let's maybe point out here that we're setting n equal to 1, and we'll just make the quick observation that 3 is equal to 3, which we can write as 2 to the 1 plus 1. But that means that we have 3 divides 2 to the 1 plus 1, and that establishes our base case. Now next, we're ready to prove that the kth case implies the k plus first case. In other words, we're ready to make our induction step. So let's do that. We will suppose that for some odd k, which is bigger than or equal to 1, we have 3 divides 2 to the k plus 1. But then by the definition of divisibility, that tells me that 2 to the k plus 1 equals 3 times m for some natural number m. And now we want to move to the next case. But we want to be careful here because the next case is not the k plus first case, because if k is odd, then k plus 1 is even. So we want to look at the next odd number. So let's maybe point that out. The next odd number is k plus 2. So that means the next case we need to look at is the k plus second case. So let's maybe go ahead and do that. The k plus second case will start over here on the left-hand side, but just replace 2 to the k with 2 to the k plus 2. So let's see what that gives us. So we have 2 to the k plus 2 plus 1. Well, that's going to be equal to 4 times 2 to the k plus 1, like that. So it seems like we might be at a little bit of an impasse. But maybe we can add 0 in a certain tricky way so that this is obviously a multiple of 3. So let's see what we can do. Maybe we can add 4 to this and subtract 4 to this. And then group these carefully. So we'll group this 4 times 2 to the k with this 4, and then we'll group 1 with the negative 4. So I can factor a 4 out of the green underlying terms, and that gives me 4 times 2 to the k plus 1, and then I have a minus 3 left over like that. But from here, I can go ahead and replace 2 to the k plus 1 with 3 times m by my induction hypothesis. So that gives me 4 times 3 times m, minus 3. Then I can go ahead and factor a 3 out of that entire thing. That gives me 3 times the quantity 4m minus 1. But that means that 2 to the k plus 2 plus 1 is a multiple of 3. In other words, 3 divides 2 to the k plus 2 plus 1. And that finishes this proof. Okay, let's do another one. Our next example is another divisibility example. So we want to show for all natural numbers n that 6 divides 17n cubed plus 103 times n. What I mean by 6 dividing that, just like in the last example, that means that this 17n cubed plus 103 times n is a multiple of 6. So let's jump right into it. So our base case is going to be the n equals 1 case. To be honest, sometimes you'll use the n equals 0 case, and clearly 6 divides 0 because 0 is divisible by anything, but here we'll take n to start at 1. So let's see what we get here. We'll have 17n cubed plus 103n. That's equal to 120 if n is equal to 1. But 120 is equal to 6 times 20, from which it follows that this object is divisible by 6. So we've established our base case. So now let's do our induction step. So we'll assume that this is true for some k and use that to show that it's true for the next value of k. So let's say we suppose for some k bigger than or equal to 1, we know 6 divides 17k cubed plus 103 times k. Now we'll unravel what that divisibility relationship means via multiplication, so it's a little bit easier to calculate with. So we'll say, so 17k cubed plus 103 times k equals 6 times m for some natural number n, m. Now we'll go ahead and look at the k plus first case. So I'll write it like this. Let's consider 17k plus 1 cubed plus 103 times k plus 1. Now let's do some calculation on that, and hopefully we can use our setup to show that that is a multiple of 6. So we can multiply out this binomial, so k plus 1 cubed. Well, you can just look up the binomial expansion formula or multiply it out by hand. Either way, you'll get 17 times the quantity k cubed plus 3k squared plus 3k plus 1, like that. And then over here we have, this is plus 103k plus 103. I'll go ahead and distribute that through. So next what we'll do is multiply this 17 through and start to combine like terms. And by combine like terms, maybe I'm thinking about these two terms as being terms that might be important to combine. Okay, so let's see what we get. We'll have 17k cubed plus 103k. It's important to keep those together because they are from our induction step. Then let's see what we have after that. So we'll have 17 times 1 plus 103, so that'll be plus 120. That's what we get for the numbers. And then what we have left over is plus 17 times 3k squared plus 3k. So let's see what we can do with this. We know that this is equal to 6 times m. This is equal to 6 times 20. So I can take that whole thing and write it as 6 times m plus 20. So just to reiterate, that's from all of this. And then we're left over with this 17 times 3k squared plus 3k. I'm going to tweak that a little bit and write it as 17 times 3 times k plus 1. Now I'm going to argue some things in words that you would need to write down in your proof, but since I'm presenting on the chalkboard, instead of writing down, I won't write it down. What we know is that regardless of the parity of k, exactly one of k or k plus 1 is even. So maybe I'll just sketch that in here. So 1 is even. and I don't mean the number 1, I mean one of those numbers is even, k or k plus 1. But the one that is even can be written as 2 times some other number. But then you can take that 2, combine it with this 3, and you've got that is a multiple of 6. So now we can write this as 6 times capital M, where that comes from combining this bit right here along with this extra bit right here. But that finishes it off because we've shown that the k plus first case is a multiple of 6. In other words, 6 divides the k plus first case. So our next little example will have to do with the Fibonacci numbers. So let's recall their definition. So you've got 2 seeds, f sub 1 and f sub 2, they're both equal to 1. And then you have our 2-step recursion, which is pretty famous, and that's f sub n plus 2 equals f sub n plus 1 plus f sub n. And what we want to do is show that the sum of the first n Fibonacci numbers is equal to f sub n plus 2 minus 1. And since this is a whole video about induction, we'll use induction. So let's first do our base case. And so notice for our base case, that'll be the n equals 1 case, which means we need to calculate f sub 3. So maybe we'll just notice real quick that f sub 3 is equal to f sub 2 plus f sub 1, which is equal to 2. And that's by our recursion and our 2 seeds. Great. And now we can write f sub 1, well, that's equal to 1, which is equal to 2 minus 1, which is equal to f sub 3 minus 1. And that establishes our base case. So now let's jump into the induction step. So we'll suppose this is true for some k. So let's suppose for some k bigger than or equal to 1, the sum of the first k Fibonacci numbers equals f sub k plus 2 minus 1. And then as we've been doing, we want to take the left-hand side of this equality and look at the next case and use our induction hypothesis to prove that the next case follows. So here we'll write consider f sub 1 plus all the way up to f sub k plus f sub k plus 1. We can think about these first k terms as being grouped and then apply the induction hypothesis to these first k terms. So that leaves us with f sub k plus 2 minus 1 plus f sub k plus 1. So let's maybe notice that these are being grouped from our induction hypothesis, and then this guy is just coming along for the ride. Okay, now we can apply our recursive definition. So we know that f sub k plus 1 plus f sub k plus 2 will be equal to f sub k plus 3. So this is equal to f sub k plus 3 minus 1. But that's exactly what we want it to be in order to establish this formula. And so that finishes this proof by the principle of mathematical induction. Okay, I'll get rid of this and we're going to do one more example. For our last example, we're going to look at a pretty classic geometry result. So we want to show for n bigger than or equal to 3, the sum of the interior angles of a convex n-gon is n minus 2 times pi. So you can take convex to be defined several different ways. So maybe I'll let you guys look up your favorite, but what we'll think about is that all of the interior angles are less than 180 degrees, or pi radians. Okay, so since we only want to prove this for n bigger than or equal to 3, because for n-gons the triangle is maybe the smallest one that's of any interest, then that'll be our base case. So let's look at, like I said, our base case, which here will be the n equals 3 case. And so that means we want to start with the triangle. So I'll just draw my triangle like this. I'll label these angles alpha, beta, and gamma. What we want to do is show that alpha plus beta plus gamma is pi. So it's well known that the sum of the interior angles of a triangle is 180. And I don't know how far we want to go back in geometry to prove this, but I'll at least go back one step. So how do you prove this result? So you want to introduce the unique line which is parallel to this base and goes through this vertex right here. So maybe I'll draw that in yellow. So there's my unique parallel line. So maybe I'll put a little arrow on it. I think you can do that to show that they're parallel. So next we'll extend these line segments which form the sides of the triangles like that. And then there are some well-known geometry results that say that this angle right here, alpha, is the same as this angle right here, alpha. And then opposite angles are equal. Great. And then this angle beta is the same as this angle right here, beta. And then again, opposite angles are congruent, so that's the same. Next, we see that this yellow line is a straight line, which means it makes a 180-degree angle or a pi radian angle. But on the other hand, its measure is alpha plus beta plus gamma. So from that, it follows that alpha plus beta plus gamma equals pi, which is equal to 3 minus 2 times pi. And that establishes our base case. So like I said, we could go way further back in terms of proving geometric results, but I think maybe this is far enough back. Okay, let's get rid of this and we'll look at the next step. Okay, now we're ready to make our induction hypothesis. So we want to suppose for some k bigger than or equal to 3, the sum of angles of a k-gon is k minus 2 times pi. I've left some words off there like convex and interior angles, but you can add those. Okay, now we want to look at the next case. So let's consider a convex k plus 1 gon. So let's maybe write that down with vertices a1 through ak plus 1. So let's say our vertex a1 is here. Our vertex A2 is here, vertex A3 is here. Now let's go from the other direction. Say this right here is our vertex AK plus 1. This right here is our vertex AK. This right here is maybe our vertex AK minus 1. And then obviously we can't draw everything because K is arbitrary, so we've just got a bunch of vertices in the middle here like that. Now we want to break a triangle away from this and then apply the induction hypothesis. Okay, so let's see if we can do that. So we'll break this triangle away right here, and then we can jump to using our induction step. So let's notice the sum of angles of the k plus 1 gon equals the sum of angles of the k gon plus the sum of angles of triangle A1, AK, AK plus 1. Because we've broken this into a k-gon, which maybe I'll shade in blue like this, and then a triangle, which I'll shade in green like that. Okay. But by our induction hypothesis, we know that the sum of the angles of the k-gon is k minus 2 times pi. Then by our base case, we know that the sum of the angles of a triangle is pi. So adding those together, we get k minus 1 times pi, which is exactly what we need it to be to finish this induction proof. And that's a good place to stop.